All right, folks, let me take a couple minutes to show you actually how easy this was, and I'll point out where I made my mistake. All right, so the diagram I have here is we have a box, but it's empty. There's the case. I tried to put some weight in it, but I don't know what the force of buoyancy is yet. So what we do is we start with an empty volume. In this case, if we have an empty box, then we are going to still have, if I have the empty box, so think of it as a thin wall plexiglass box that's full of air. It can be vacuum, but it's basically just an empty box, so it doesn't weigh anything. So we're going to have F1 due to it acting on top of it, acting downward. And then since there's fluid underneath it, the fluid is actually going to be acting upward with a force of F2. And then because we're trying to hold this under the water, or whatever liquid, let's assume it's water, we have something called the buoyancy force. All right, and then the key thing, of course, is that this volume here is empty. So, and it doesn't weigh anything. So now when I do my sum of the forces in the y direction, we have minus FB minus F1 plus F2, and all of that equals 0. So now we go ahead and we solve for FB. So FB is going to equal F2 minus F1, and then we're saying that it's hydrostatics, so the force is going to be proportional to the specific weight, rho GH, times the area. So we have gamma times the area times H2, and we subtract off of that gamma times the same area because it's a cube minus times H1. So now we get this is going to equal gamma A H2 minus H1, which equals gamma times the volume of the cube. So let's do this again, but now let's say that there is a sphere. I'm going to draw a circle, but let's assume that it's a sphere. Make it a little bigger, easier to see. And what we're going to do is draw a cube around this. All right, so inside the sphere, it's again going to be empty space. But now, the reason why we're going to put the cube in will be evidence, but if we look at what's left over in between the empty sphere and this outer cube, there's going to be water in that, or the fluid. So we're going to have to account for that. And we're going to want to know what the weight of that water is. So the weight of the water, or the weight of the fluid, let me just do F, is going to be equal to gamma, right? That's going to be the specific weight of the fluid. But now volume of that fluid is the volume of the cube minus the volume of the sphere. So this will be volume of the cube minus the volume of the sphere. All right, so then let's just propagate gamma through here. So we have gamma times the volume of the cube minus gamma times the volume of the sphere. All right, so let's just add in the rest of our forces onto this diagram. So again, we have an F1 acting on the top and F2 acting on the bottom. And now we have the F buoyancy force, but now there's also the weight force. And I'll just put it out here and make it in black so that we're not confusing it with the weight of the sphere or anything like that. So let's go ahead and now do our static analysis. So sum of the forces in the y direction. So just like before, it'll be minus FB minus F1 plus F2, but now we have minus the weight of the fluid. And again, all of this has to equal 0. So again, we can solve for FB. So FB will equal F2 minus F1 minus the weight of the fluid. Well, we have an expression for the weight of the fluid now, so we can go F2 minus F1, and we're going to go minus gamma volume of the cube plus gamma times the volume of the sphere. All right, so we know from before that F2 minus F1 is going to be gamma times the area times H2 minus H1 and volume of the cube plus gamma volume of the sphere. All right, and then we should recognize that this term here is simply gamma times the volume of the cube. So these two terms cancel with each other, and we're left with the expression for the buoyancy force as being FB equals gamma times the volume of the sphere. So this result holds true for no matter what shape we put under the surface. So what we conclude is what the buoyancy force is known as. So the force of buoyancy is equal to the specific weight of the fluid times the volume of the displaced fluid. Okay, so sorry I couldn't have done that while we were in lecture, but hopefully it makes more sense now. All right, see you all on Wednesday.